Okay, we can maybe start 1 minute before the schedule. I think it's not a problem. So it's my pleasure to introduce the last speaker of this morning section, Adrián Andrada from Córdoba, Argentina, and he will talk about canonical bundles of compact hypercomplex or manifold.
Okay. Okay. Thank you, everybody, for being here. First of all, I would like to thank the organizers for giving me the opportunity to give this talk. I'm more than thankful. I'm very happy to be here, yes, with many friends and many important geometers, and I'm really happy. And I also would like to take the opportunity to thank the organization and the sponsor for the financial support you have given to many young people from Argentina. And I think that this will be very stimulating for the geometry in Argentina in the near future, I hope. So thank you, and let me begin. This is joint work with Alejandro Torcacher, a former student of mine who has finished his PhD in December last year, and who, by the way, is having his birthday today, so everybody can greet him after the talk. And well, and these results I'm going to talk about are all in this article, so when there is no reference mentioned, it will come from here. And this is the only talk on this conference on hypercomplex manifolds, I guess, so I hope you find it interesting. And, well, let us begin. Well, this is something very basic that everybody knows. We have in a smooth manifold a complex structure. It's an endomorphism of the tangent bundle such that its square is minus identity, and together with the vanishing of this noise, I don't know how to pronounce that, tensor, Nijenhuis for us. Well, this is the definition of the noise tensor, and this is equivalent, of course, by the Nylander-Nirenberg theorem to the existence of a holomorphic atlas on this smooth manifold, which makes it a complex manifold. By a Hermitian structure, we mean a pair of a complex structure and a Riemannian metric, which are compatible in this sense, so that J is an orthogonal endomorphism, but it's, again, it will be a skew-symmetric endomorphism also of this metric. And given a Hermitian manifold, there is always a unique connection, nabla B, which satisfies these conditions. It is metric, and it's Hermitian. It preserves both the complex structure and the Riemannian metric. And the contraction of the torsion of the connection with the Riemannian metric gives us a three form. This is, what is this? Okay. This is known as the bismuth, or more recently also as the Strominger connection, and it is given by this formula, where this torsion three form is given by this, where omega is the fundamental two form determined by the Hermitian structure. So, well, that was the introduction, only complex manifold. Now we move to the main object of study, which are the hypercomplex manifolds. So, there could be different ways to define this kind of manifolds, but we follow this one, which was given by Boyer, Charles Boyer, in the 80s, I don't recall very well. But we will understand by hypercomplex structure on a smooth manifold, it will be a set of three complex structures, J1, 2, and 3, which satisfy the relations of the quaternions. So J1, J2, anti-commute, and J3 is this common product. In particular, when we have this, the real dimension of the manifold, of the smooth manifold underlying this, it has to be a multiple of 4. and it is each tangent space is a H module for each P. These are also the underlying manifolds of the Hypercomplex manifolds, which have appeared several times in this conference. But in this talk, the Riemannian metrics will not play a very important role. We will concentrate only on the hypercomplex condition. An important feature of these structures is that given this family of three complex structures, we can define many other complex structures on the same manifold. Indeed, a two-sphere of them, because you can take any point in the two-sphere, A1, A2, A3, and then you take this linear combination of the complex structures, and this one, which is I call J sub A, is again a complex structure on the manifold. In fact, the important thing is the whole sphere of complex structures. It's not the real hypercomplex structure, but well, we have to work with some specific ones, so we choose this J1, J2, J3. Sorry. Okay. An example, a standard example is consider in this n copies of the quaternions. We do like we always do with C to the n. So now, but each quaternionic gives us 4 real coordinates. So Q1 to Qn gives us these 4n real coordinates, where each quaternion is written like this: XL, YL, BL, WL. And then we can define in a very natural way 2 complex structures. One sends the x's to the y's, and then v's to the w's. The other one x's to the v's, and y's to minus w, and the other one is the product of this. This is very natural, the standard one, but clearly it is non-compact. Berger gave the classification of 4-dimensional compact hypercomplex structures, manifolds, I'm sorry, and they are 4-dimensional tori, K3 surfaces, or quaternionic Hopf surfaces. This is the only dimension in which such a classification is complete. In the case of the hypercomplex surfaces, which would be real dimension 8, that classification is not known, and I guess it's still far from being complete. So any new result on that direction, it would be very interesting. Then, in this paper by physicists, Spindel and don't remember the others, it's shown that every compact Lie group of dimension multiple of 4 admits a left invariant hypercomplex structure. If you begin with a compact Lie group whose dimension is not a multiple of 4, you can multiply by suitable toras so that you can have one of these. And then Joyce gives another proof of this previous result using root decomposition, suitable root decomposition, and then also extend it to compact homogeneous spaces. For instance, you have this example or this family of examples. And some other examples with people who are here, Barberis, Laura gave a classification of 4-dimensional Lie groups.
Sorry, did Joyce prove that any 4n-dimensional homogeneous space compact?
No. That he gives example. Yes. Then Barberis gives this classification of 4-dimensional Lie groups admitting a left invariant complex structure. Then Dottifino, a little later, 2003, gives a classification of, in dimension 8, of nilpotent Lie groups with a left invariant hypercomplex structure. And they are all two-step nilpotent. In this, all of these admit compact quotients, so we obtain compact examples. In dimension 4, the only compact examples are the torus and S3 times S1. And then, well, you can see. It was very active, this part, also with many works of Misha Verbitsky. There were many results in this part, in this time of the century, the beginnings of this 21st century. Then maybe there were less papers on this topic, but then they started again in 2017 or 15. We also worked with Misha and Aleska and with some other results that gave a new emphasis to this topic. And I guess it's very interesting. Then let me remind some other things. Here we have some metrics. A hyperharmonic structure is now a hypercomplex structure together with one Riemannian metric which makes all of these pairs, J alpha, together with this metric, Hermitian. You can always produce some kind of such a Riemannian metric. As particular cases, we have the well-known Hypercomplex manifolds. That happens when all of these Hermitian structures are indeed Kähler. And, well, in this case, we have we know that the holonomy of the Riemannian, the Levi-Civita connection is in SPN. Well, the manifold is 4n, the dimension is 4n, so that the metric has to be Ricci flat. But there is another condition which is very much used in this setting, which is the Hyperkähler with torsion condition, which is a weaker condition than Hyperkähler. That's maybe too strong. You consider, to define it, you consider the associated fundamental two forms obtained by this metric G and the complex structure J2 and J3. You combine them into this one, big capital omega, and you take the Dolbeault derivative of this, the del omega equal to 0, where del is with respect to the complex structure J1. So, obviously, Hyperkähler manifold is also HKT, but there are many other HKT manifolds which are not Hyperkähler. Well, in dimension 4, all of them are always HKT by a result of what we've shown and taught.
Is that condition symmetric for J1, J2, and J3?
Yes.
Now it is. Because of this result of Lancharov and Poon, you can, this HKT condition, you can see happens if and only if the bismuth connection of all each single complex structure with this metric G, all of them coincide. So that makes it symmetric. And initially, it was believed that any compact hypercomplex manifold admits one of these metrics, HKT metric, but Fino and Grancharov proved that conjecture in 2004, exhibiting a compact hypercomplex manifold which does not admit any HKT metric. The example is, in fact, 8-dimensional in manifold, and in order to prove this, they use the Belgun symmetrization process. And then later, Barberis, Dotti, and Verbitsky, they also characterize which hypercomplex in manifold admits an HKT metric. Okay. Sorry.
With your notation, capital omega is at 2,04 with respect to J1 or 0,0?
Yes, 2,0 with respect to J1. Yes. Yep. Well, One more thing. One could also have defined hypercomplex manifolds trying to use an atlas. So consider, for instance, if you have a, sorry. Here. What is this one? Okay. Assume that M is for n-dimensional and it admits an atlas whose charts satisfy that the transition functions are in fact holomorphic with respect to all the complex structures in a fixed standard hypercomplex structure on R to the 4n, which can be identified with the quaternions to the n. Then it is easy to see that that hypercomplex structure on R to the 4n goes to the manifold and it gives rise to a hypercomplex structure there. And they are called locally flat, and they deserve a special name because not every hypercomplex structure is of this kind. So there is nothing similar to this Nylander-Nirenberg theorem in the hypercomplex manifold. So the definition using charts and the definition using the tensors are not equivalent. Okay. So indeed, Somes this was previous to the definition of hypercomplex manifold, but never mind. Every locally flat hypercomplex manifold is affine. That is, these transition functions are restriction of affine transformations of R to the 4n. So, and there are examples which are not locally affine, for instance, this one. Some K3 surfaces and the examples of Joyce. How can we tell if one hypercomplex manifold is locally flat or not? Well, there is something extra, the Obata connection. Obata proved that, with another names, with another notations, but in the notation I'm using now, he proved that on any hypercomplex manifold, there exists a unique torsion-free connection which preserves all the complex structures. This is the Obata connection, and it can be given by this formula. Previously, there was a much more complicated formula given by Markiafava and Alexevsky, I guess, but it was very complicated with very sums. But recently, Soldatenkov, which I guess is here, proved this much simpler expression, which we can work with this much easily. And it was proved by Obata that this hypercomplex structure is locally flat if and only if this Obata connection is flat. So computing the curvature of this connection tells us if the hypercomplex structure is locally flat or not. And again, since we have to talk about holonomy because of this conference of special holonomies, this condition here says that the holonomy of this Obata connection is contained in this group GL and H, which is given by these operators in GL4n, which commute with all the complex structures. Also, it is interesting to find hypercomplex structures such that the holonomy falls inside the commutator subgroup of the general linear quaternionic group, SLNH. Both of these groups appear in the list of Merkulov and Schwarzhofer, how it is pronounced, of the irreducible holonomies of torsion-free connections. So people were trying to find examples of manifolds where the holonomy is here. These ones have some special properties, and they are, in this case, they are called like this, SLNH manifolds. Well, as I told you before, this is a condition that you have the holonomy of the Obata connection inside SL, which is the commutator of this group. and they were studied by Babitsky, Grancharov, Ivanov, Weber, Lechmy, Tardini, Gentili, Vezzoni, Fino also, I forgot. And one particular property of these manifolds is the following given by Babitsky, which has to do with the rest of the talk. He has shown that if we have one of these SLNH manifolds, then the complex manifold obtained with M and fixing any of these complex structures has holomorphically trivial canonical bundle for any of these complex structures. And then there is also a question in that same paper that if we have a compact hypercomplex manifold, and assuming that one of these complex manifolds has trivial canonical bundle, does it follow that the holonomy of the Obata connection is inside SL? There are some results where this is true, some cases where this is true. For instance, Misha also proved in that same paper, I guess, that when M admits an N only one, HKT metric, this can be answered affirmatively. And also in the case of nil manifolds, which are endowed with here, with an invariant hypercomplex structure. So I have a left invariant hypercomplex structure on the nilpotent Lie group N, and then we consider the induced one in the quotient. This was proved a little later by Barberis, Dotti, and Babitsky. About these hypercomplex nil manifolds, what are the key facts that they use to prove this? First, they show that any nil manifold equipped with a left invariant complex structure has always trivial canonical bundle. And moreover, the trivializing holomorphic section can be chosen to be left invariant. And then if we have a hypercomplex nil manifold, then they took one of these left invariant trivializing sections of one of the canonical bundles, and they showed that it happens to be parallel with respect to the Obata connection, and this implies the reduction of the holonomy. So, sorry. If there is any question, don't hesitate and interrupt me, please. Here we have used the word nil manifolds. There is another one very similar, which are the solved manifolds, which is when we replace the Lie group, nilpotent Lie group N by a solvable Lie group. So the natural question is, what happens with hypercomplex solved manifolds? So, but if we follow this argument, we see that the same happens if we consider a hypercomplex solved manifold where one of the canonical bundles has a left invariant trivializing section, because it's the same sketch of proof. So the same proof works, and we also have that the holonomy of the Obata connection is inside SL. But as I said before, every nil manifold with a left invariant complex structure has trivial canonical bundle, but that does not happen for complex solved manifolds. So it is not always true that the hypercomplex complex solved manifold has such a left invariant trivializing section. So this will motivate this. Well, I will recall a little bit about submanifolds, and then I will talk about the canonical bundle of a complex solved manifold where the complex structure is induced by a left invariant one. So by a solved manifold, I mean a compact quotient G over gamma, where G is a simply connected solvable Lie group. Gamma is a discrete subgroup. We will call such a subgroup lattice. And well, if G is nilpotent, then we have a nil manifold. There are many properties about the topology of these manifolds. For instance, the first fundamental group is the lattice itself, and the other higher dimensional homotopy groups are 0. And moreover, the submanifold is determined by its fundamental group, let's say. If we have two lattices in two solvable Lie groups, such that the lattices are isomorphic as abstract groups, then the submanifolds are diffeomorphic. So that is very strong. Some facts about lattices. If G admits a lattice, then it has to be unimodular. That was proved by Milnor. This means that the trace of the adjoint operators is 0 when considering at the level of Lie algebras. Hattori also proved that if G is completely solvable, this means that the operators at X only have real eigenvalues, then the ramp cohomology of the submanifold is given by the cohomology of the Lie algebra. So in fact, it is independent of the lattice. This generalized some results of Nomisu for the nilpotent case. And, well, as Andre mentioned in his talk, it is quite difficult to construct lattices in general Lie groups. So there are some criteria for nilpotent Lie groups or for almost abelian Lie groups, but in general, it could be quite difficult. There is a result that we will use later. Well, we don't have to understand everything of this, but this result of Yamada allows us to produce some lattice in a solvable Lie group of this form. An abelian subgroup acting on a nilpotent one, the nil radical. And if we get some rational basis of the Lie algebra of the nil radical and another basis of this abelian part such that the action has a derivative with all the entries integer numbers, in some way, we can produce a lattice there. It's not easy, but we have to use also number theories, several things, to work a lot with polynomials, but I will show you later that it can be done. But now, I will move to the canonical bundle of complex submanifolds. By complex submanifold, I always mean a submanifold equipped with an invariant complex structure induced by one at the level of the Lie group, left invariant. But there are differences with the complex Lie manifolds. Why? Because the same as Lie manifolds, there are complex submanifolds which admit an invariant trivializing section of the canonical bundle. A classification of such Lie algebras in dimension 6 was given by Fino, Otal, and Ugarte in 2015. But there are another ones. There are complex submanifolds which do not have holomorphically trivial canonical bundle. For instance, some Minow surfaces or LG Klaus-Thoma manifolds, which were defined in terms of number theory of number fields, but then they were shown by Kasuya to be submanifolds. But then, how can we tell if we have a complex submanifold? How can we say if they have a holomorphically trivial canonical bundle, be an invariant trivializing section? And we have this result. This was the first result with Alejandro in that paper. A 2n-dimensional Lie group, not only solvable, any Lie group, with left invariant complex structure admits a left invariant non-zero holomorphic N0 form if and only if this one form defined in terms of the complex structure and the Lie algebra structure vanishes identically on the Lie group. What color is this? Red or green? I don't see. Red? Okay. This, I don't see very well that. So this one form in red will appear a lot of times in this talk. And I that had already appeared in some papers by Kosul for the homogeneous cases or something like that, but here we have this. Note that if we want lattices, the Lie group has to be unimodular, so this part, the trace of this adjoint operator is 0, so we have only the first part. In any case, well, if we have this case where this vanishes, any compact quotient by discrete subgroup will have also trivial canonical bundle. The trivializing section descends to the quotient. Well, sketch of proof, this is simple, but because in any Lie group equipped with a left invariant complex structures has a section of the in N0 form which is non-vanishing, but that is only a smooth section, trivializing section of the canonical bundle, not necessarily holomorphic. Any other section will be a multiple of this, but we want it invariant, so we only, to see if it's holomorphic, we have to set this equation, d sigma equal to 0, and then after long computations, we have to the previous result, that is the vanishing of this one form.
Is this condition the same as, so you have the complex structure, you consider the 1-0 part of the complexification, and it is unimodular, it's the same?
When it is, when the Lie algebra is unimodular, the Lie group is unimodular, it's equivalent to both subalgebras G10 and G01 to be unimodular again. That's right. And a corollary is that if G admits an abelian complex structure, which are those satisfying this, they all, and if it has a lattice, then the canonical bundle is trivial. These complex structures have appeared a lot lately in these studies. What else? However, there is some, I think, a new phenomenon, because there are some complex solved manifolds with canonical bundle which is trivialized by a section which is not left invariant. For instance, we can consider this four-dimensional Lie group. It's an action of R on the Heisenberg. We have this complex structure, and it does not admit a closed to 0 form, a left invariant one, because the canonical form of the theorem is not 0. It's this one. But anyway, if we go to the manifold level, this Lie group is R4, and in these coordinates, we have that E0, the one form E0 is dt, and if we set tau, this function x of it times the left invariant 2-0 form, then we derive, is okay? Yeah. And then we obtain 0. So it is holomorphic and closed. And moreover, this admits lattices. For instance, we can consider this lattice, and this lattice is invariant by, no, sorry, the form tau is invariant by the lattice, so it descends to the quotient, so we have a nowhere vanishing closed to 0 form on this solved manifold, and then it has trivial canonical bundle. Okay. Well, so we need to start to study these kind of things. So we will restrict now to a solvable case, and we were able to show with Alejandro that, in fact, no, sorry, this one. Any 2n-dimensional simply connected solvable Lie group equipped with a left invariant complex structure admits a nowhere 0 closed N0 form tau. That happens for every complex structure on a simply connected solvable Lie group. That means that the canonical bundle of this Lie group is trivial. It's clearly non-compact. But, well, we were able to prove that after a very long time of thinking. This is a consequence of the following lemma. which is, I think that it is of interest. Well, there is some relation with the nil radical and the kernel of this canonical form psi. And we used that there is a special basis for 1-0 form satisfying some relations. That one of them, the real parts are closed up to a certain number, a certain index, and then the dual vectors of this real and imaginary part fall in the intersection of the commutator and its image by J. Well, if it's left invariant, okay, we are done. If not, we can multiply it by a function to make it. It will not be left invariant, but then it will be closed. So it's not necessarily left invariant. And in most cases, it's not left invariant if this form is non-zero, it will be non-invariant. So, well, and using this basis, we can produce a one form which combined with this one gives us a function I will not write much, but we can find the function we needed to multiply the left invariant one to make it closed. But well, this happens for any simply connected solvable Lie group, even if it's not unimodular.
I'm sorry, I'm just confused about something. Are you asking about the triviality of the canonical line bundle on the universal cover, or?
No, this is simply connected.
Right.
But
I'm saying, I thought you made some statement about Hopf surfaces, and Hopf surfaces, the canonical line bundle is certainly not holomorphically trivial, right? Otherwise, you'd have a closed.
No. Yes, it's.
What?
Yes, the Hopf surfaces do not have a trivial canonical bundle, but yes, if we have a trivial canonical bundle here via left invariant holomorphic section, then this holomorphic section descends to.
If it's invariant, sure.
Yes.
I'm just. You made some statement about Hopf surfaces as examples of hypercomplex manifolds, and I was just very confused because those are already examples where the canonical line bundle is not trivial.
Yes, but no, but I gave them only as an example. I did not say anything about the canonical bundle of the quaternionic surface, I guess.
There was some general theorem about the canonical line bundle was trivial under some circumstances. I just misunderstood, I'm sure.
Maybe this one? Or?
It's okay.
Okay. Sorry.
I seem to have missed something, though.
Okay. Okay. So, we have here this that any simply connected solvable Lie group has a trivial canonical bundle, but this holds for any general Lie group, maybe even if it's not unimodular. But well, if we want to go to a quotient, since this trivializing form is not necessarily invariant, it probably will not go to the quotient. It will not descend to the quotient. It has to be compatible with the lattice. So in some cases, we are able to find examples of these trivializing forms which are compatible with some lattice, but in other cases, it's not possible. Because there are some abstractions. There are abstractions for the triviality of the canonical bundle of a solved manifold. Because of this theorem. If we have a simply connected Lie group with left invariant complex structure and a lattice, if the compact quotient with the induced complex structures has trivial canonical bundle, then this happens. Trace of J of the commutators here is always 0. This means that the one form from the theorem from before, from the previous theorem, has to vanish of the commutator ideal, or equivalently, that it has to be closed. So, in this sense, if we have a simply connected Lie this is not necessarily solvable, it's more general. But if we have one of these Lie groups with left invariant complex structure, and then this does not happen, then any quotient will not have trivial canonical bundle. So that's the abstraction. Well, oops, I'm late. So, well, I will skip the proof, but here this again uses the Bell-Gould's symmetrization process and uses a result by Bessoni that this form is the Chern-Ritchie form. This two form is the Chern-Ritchie form of the Hermitian structure with this J and any left invariant Hermitian metric we put on the quotient. So, well, but I don't have much time. So this is abstraction. But in other cases, this I will also skip it because I want to go to hypercomplex of manifolds. So there are abstractions for the triviality of the complex, of the canonical bundle, but there are other examples where we are able to find sections which are compatible with lattices, and they go to the quotient. So why to study hypercomplex of manifolds? Because they are the natural generalizations of hypercomplex in manifolds. A first example was given of a hypercomplex solved manifold, was given by Barberis and Fino in 2009, and it has dimension 12. But I don't know if there was another one. Well, but with Laura, very recently, we gave a classification of 8-dimensional, almost ideal 8-dimensional solved manifolds, hypercomplex. I mean, I forgot the word hypercomplex. So, and there are not many. There are only two possible Lie algebras. One of them is nilpotent. The other one admits a Hypercomplex metric, and that's it. And also, I could do that because I like them, and it's interesting to study these kind of things, but they are not easy anyway. But what happens with the canonical bundle now of hypercomplex of manifolds? If recall that we have two spheres of associated complex structures, and we can prove that in this case, if with one of the complex structures, this solved manifold has trivial canonical bundle via an invariant section for some alpha, then it has trivial canonical bundle for all the complex structures in this two sphere, also with a left invariant section. But what happens in the other cases when for instance, one of them has trivial canonical bundle via a non-invariant section, and if I'm not wrong, it's what happens here. I will show you an example of an 8-dimensional hypercomplex of manifold which behaves in different way for each complex structure. And for this, I'm happy that I'm using a construction that I gave together with Simon Salomon in my first paper, 2001, I guess it was. It was a machinery to produce hypercomplex Lie algebras. If we begin with a 4-dimensional Lie algebra, it's an extension of the Heisenberg with these brackets. We consider a particular complex structure here, and we note that there are two subspaces, this G plus and G minus, which are, in fact, both subalgebras. This is abelian, this is not. And moreover, one of them is the image of the other by the complex structure. In this setting, we had shown that we can complexify this Lie algebra and then consider it again as real. And this Lie algebra, G hat, admits a hypercomplex structure. Which are the J's involved? This J2 is simply the extension of the original one. And the second one, well, J1 in this case, is given by multiplication by I, because we are in the complexification, but we change the sign in half of the Lie algebra on this G minus. Explicitly, we have, well, this is eight-dimensional. We have a lot of, well, the description of the complex structure and also the description of the Lie brackets. But note, note that this is R2 semi-direct product with the nilpotent Lie algebra, the complex Heisenberg algebra, three-dimensional complex. And we can use this theorem of Yamada to prove that there is a lattice. It's not so easy because we have to take some strange numbers here, but which are well known in the construction of lattices. We have to use this pi here and certain lattice in this nil radical. But if everything is okay, it all fits well. We have a rational basis, and the action is via integer matrices. So there is a lattice. But if we want to consider what happens with the canonical bundles of the complex structures, we consider these canonical bond forms, and then we can compute none of them vanishes. Psi 1 is a multiple E8, and then, well, we have these other two. Since they do not vanish, there are no left invariant trivializing sections of the canonical bundle for any alpha. And moreover, the last two, psi 2 and psi 3, do not vanish identically on the commutator subgroup, commutator ideal. So because of the obstruction seen before, these do not have, with J2 and J3, they do not have trivial canonical bundle. What happens with J1? We can consider this 4-0 form with respect to J1, which is left invariant, given in terms of the basis by this. We go to the Lie group. We have real coordinates. The Lie group is simply R8. And if X8 and X4 have to come from the, where is it? This R2 here. Those are the two outside which are acting on the nilpotent ideal. And in the real coordinates, if we consider this function, exponential of 2 times I, this coordinate x8, this will be invariant by the lattice, and it can be seen that also the derivative of f times sigma 1 will be 0. So it has trivial canonical bundle. And therefore, one of them has trivial canonical bundle, the other two don't, and then this example cannot have Obata holonomy containing SLNH, because if it did, all of them would be trivial. So if everything is okay, it provides a negative answer to Verbitsky's question. Well, and just to finish, oops, late. Final remarks. Well, using previous results, we also see that this hypercomplex on manifold cannot admit any HKT metric. We also computed the Obata connection, and it is flat in this case. More recently, we have been able to generalize this example to any dimension. It's a quite simple, straightforward extension. It can be done. We believe that Verbitsky's question remains still open for a hypercomplex manifold, such that all of these complex manifolds have trivial canonical bundle. We tried to produce an example of this with soft manifold, and it was impossible because you have to find 3 different functions that makes this left invariant form closed, but these 3 functions have to descend to the quotient, so they have to be compatible with the lattice, and it's quite difficult. Very recently also, Gentili and Tardini have shown that hypercomplex or manifold is SLNH if and only if one of them, this canonical one, have an invariant trivializing section. And even more recently, Fusi and Gentili have proved that the SLN condition is equivalent to the holomorphic triviality of one of the canonical bundles, and together with the existence of a quaternionic Gaussian metric, which can be defined in terms of the hyper-Hermitian structure. But, well, this is it, and thanks for your attention.